Do I get a green light? Thank you. My assistant Lawrence in the background there. Well, welcome, ladies and gentlemen, to our next lecture. You are going to be very familiar with the words I'm about to use because we have to say them every time, because some years ago somebody complained that the only fire exit in the place wasn't pointed out. Anyway, I have to draw your attention to the fire exit, which is the one that all you've just come through. We're not expecting any fire alarm tests today, so if you do hear a fire alarm, it will be the real thing, and please make your way to the car park and assemble there. Usual business, and no recording of lectures is allowed either as video or audio, except for Lawrence at the back there, because this will eventually appear on the RSGB website. Please set your mobile phones to stun, or off, or turn them to silent. And have you bought your DXpedition raffle tickets? No? No? Right, don't forget to buy your DXpedition Fund raffle tickets, and lunch tickets is irrelevant now. So, here we are, gathered. I have to turn over the page. I laminated it this year because I'm always putting it down and forgetting it. An introduction to SDRs and GNU Radio, then with Heather.
Okay. So I'm going to try and whiz through this. There's a lot of slides, and at the end I'd like to do a little demonstration, but basically we're just going to do 4 sections, look at, it really is an introduction, but hopefully with a bit of science behind it to interest some people. I know I can't really get away with using this. Can anybody over that side see this thing? No one can see that. Okay, I'll give up with that. So software-defined radio, somewhere in the whole system we're going to have some software, and that's really as good as you're going to get for a definition. It's really about where you put the ADCs, where you turn your analog signal, be it RF, IF, audio, into a digital signal that you can then do some software on. That really is as good a definition as I think you're going to come up with. So very quickly we'll have a look. If you put an ADC in at the AF, probably familiar with the BHI devices that do a lot of nice signal processing on your audio to make it sound much better. All sorts of people have noise reduction, filters, all that sort of good stuff in the radios you're probably all familiar with. This guy, Warren Pratt, he's done some absolutely amazing stuff, mostly I think in Linux, but he's written some libraries that will use the voice model of the human voice to try and guess what was missing when you get a bit of code, a bit of the audio chain blanked out for whatever reason. It's well worth, if you're going to get interested in DSP applications, he's a very good place to start. Most people have PCs with sound cards. That's a good way in if you need to get into it. And some of the dynamic ranges we've got out there at the moment, this Cirrus Logic part, it's literally a couple of pounds and giving you 24 bits at 192 kilosamples. So for anyone into LF, you can actually digitize your RF with that part at 24-bit. More typical, we would put it in the IF or the RF path. We'll talk a little bit more about quadrature modulation in a minute. That's what it's all about. I don't know whether anyone's here familiar with that. Hopefully some people, but once we've got an INQ signal stream data basically coming out of our ADCs, we can look at that in programs like GNU Radio, which we'll look at in a bit, SDR Sharp, I'll show some pictures of that. And the other thing that we're probably going to need is some way of getting this data into a PC and then about inside a PC between different bits of software. So we'll take a little bit of a look at that. So one simple example, what can we do with them? I took that screenshot across 3 different monitors. It's about 1.2 meters of visible screen. And that's 2.5 megahertz of bandwidth. So you've got a lot of data, a lot of bandwidth you can do. And it's about a 600 hertz, 600 hertz resolution on that signal. So if you want to peer at it really closely on a huge monitor, and you won't get that anywhere else really without using an SDR technology. So more of what we can do. Noel did a presentation earlier on web SDRs. He's using, I think, 6 or 8 SDRs at the moment. You can do more than that concurrent channels on a single SDR, as long as you're the one with the computer that's processing. All sorts of things you can do, removing IF noise, spectrum displays we just looked at. You could put a huge averaging in there, something we've used on the microwave bands, looking at the IF. We have a 1 second average, the noise goes completely, and if there is a signal there, you can see it. These things are all very easy to do once you've got IQ data. Pre-distortion and distortion corrections, won't talk very much about that, but that's something that you can do in the digital domain that you have trouble with doing analog-wise. Diversity, and then all the 3G, 4G base station stuff, it's all SDR, it's all being done with. So, cheap and cheerful, there's a £6 from eBay RTL SDR, brilliant little piece of kit for the money, and that's all stuff that you can do on that, all for free. We've got all sorts of options there. This picture I downloaded a year or so ago. Pages, APRS, pick up the ISS, weather satellite images from the WX sats. All of this stuff I picked up with a white stick on the roof. You don't need much to do all these things. These little radios come with a tiny little mag mount antenna, which will do things like ADSB really well. So if anyone's thinking not sure they want to get into this, it's almost free. I say £6 for the radio and PC and so on. So I already showed you that little blue guy. I don't know, the SDR play, anybody? Yeah, there he is over there. Quick plug. This is a brilliant bit of kit. They're downstairs, they're selling these guys. They're a little bit more expensive than Zero. They cost £80 for one of those guys. But look at the range, 1 kilohertz to 2 gigahertz in a single receiver. There aren't many places that you can do that without having an SDR. If you haven't got a computer at all, you can get a 7-inch screen, a Raspberry Pi and a mouse and a keyboard for under £70. And if you've got a bit more money and you want to try transmitting, there's the Lime SDR Mini, which is around about £100. A little bit harder to play with than these other ones, which really come pre-packaged. But again, up to 3.8 gigahertz for £100 transmit capability. Just add PAs and LNAs, and so I want to try and dispel the myth that I probably won't succeed, that SDRs are not about knobs. Most people think of them as just things that run on computers. It's not real radio. It's only not real radio because everyone who seems to make an SDR doesn't add knobs to it. But if you go and buy some of the new ICOM, I think the latest 7600 or whatever, is an SDR radio. It's just an SDR radio that they've put knobs on. But there are these things. There's this PowerMate thing. They're a bit expensive. They're £50–60 on eBay. Or you can brew your own this Pi HP SDR interface. So once you get into it, you'll find there's a lot you can do where you can actually add knobs and get some of the real radio feel, shall we say, to SDRs. Like I said, continuous spectrum. The ETIS research, we were playing with one of those yesterday on our course. It's the high-end one, 6 gigahertz. But bear in mind that although you have got this huge bandwidth, you can do everything. You can only use a small fraction of that at any one time. So you're not going to build something that will transmit on every band at the same time. But nevertheless, compared to modern analog radios, it's really it does everything. And the other thing that catches you out, you've got to have some filters in there. These things are usually wide open because they've got such big bandwidths. And if you want to transmit anything, you're looking at fractions of milliwatts for some of these things. So you need a lot of PAs in there to get on air at 1500 watts or whatever your HF contesting is. So let's jump inside one. Just an example of some ADCs there. This is a few months old now, but 3 gigasamples a second at 14-bit, if you can afford to buy one of those. But that means you're doing direct conversion of 1.5 megahertz, gigahertz signals. Pretty much the whole spectrum that anyone other than the microwave group is going to be interested in. Signal to noise ratio, we'll talk a little bit more about that in a minute, but basically it's 6 times the number of bits. So I guess quite a few radios you'll have out there 110, 120 bit, 120 dB. So it doesn't look at the start like these radios are impressive, 86 dB for a 14-bit radio. But we'll talk a bit more in a minute about why you get a lot more out of them than you start with. Effective number of bits for people who are familiar with FM and SINAD measurements. You have noise, and usually the noise is more than a single bit transition of the A to D. So when you're defining the specs or looking at the specs of an ADC, you need to worry about what its effective number of bits are, because unless you've got the effective number of bits that you're going to need in your application, you're going to find that you're going to run out of bandwidth. Dynamic range. And this little blue guy, you'll hear him at the end of the lecture. Very clear audio, and that's in decimation, which we'll talk a little bit about in the software section later. Now, the sort of community is split. Half of them are using tuners, direct ADCs, and they put the data out on some format, usually USB. More modern ones like this Lime SDR are using the USB 3 to get up the bandwidth, so you can get, I think the Lime is going to give you 60-something mega samples per second, so it's a huge bandwidth that you can then play with, selected obviously from the full capability. Cheaper SDRs, 3.2, you can use some 100 mega Ethernet stuff, so hence the Raspberry Pi can handle a USB 2 interface, no problem. And you need a bit of power in your PC. The more you want to do, if you want to do big pan adapter displays, you're probably going to want to be looking at an i5 or an i7. A modern i3 will do some of this, but if you really want to do the number crunching, then a little bit more than your basic PC. And again, the Raspberry Pi, that's 1 4-core, 1 gig. It does stuff. It can handle some of this stuff. But basically, the other camp is to put in the FPGAs, which, as you probably know, run a lot faster for parallel operations. So 2 camps, it varies a bit, but FPGAs are what interests me anyway. So, oh dear. That's not me. Okay. So IQ modulation, this is what it's all about. This is where it gets really interesting. So the old-fashioned way, we do a mix, we put 2 frequencies together, we get the sum and the difference, and most of our analog world lives is centered around getting rid of one of those 2. Whether you're mixing up or mixing down, it's always a problem, and when you're designing a radio, that's where it gets difficult. So if we do this process, we mix with a cosine and a sine, then we only get one of those two things. The other image goes out. Mathematically, it doesn't exist. So this makes it really, really easy. If we can get an I and a Q, which is basically getting a signal mixed with a cosine and a sine, two separate signals, then if we add the two, we get the difference, and if we subtract the two, then we get the sum. And that makes life really easy, because adding two analog signals, as you know, it's just an amplifier. Or in software, it's literally just A plus B. And so that gives us this kind of thing. We feed in our local oscillator, treat it as sine, where we pass it to the top mixer. We're going to get one form of that half of that equation, mix it to with a 90-degree phase shift. Now we've turned our sine into a cosine. Now we get the other half of the equation, and if we just sum them, doing an up converter there, we get our RF, and it's exactly the same process going backwards, but we'll do most of that in software. So in pictures, there's our IF, a nice sine wave. There's our cosine of the same thing, just shifted, one, the other one. And we mix them together, we will get two signals, the sum and the difference. And of course, if we take both of those together and we mix them, we just get the one signal, in this case, the low one. And if we go the other way, we get the high one. This was all done in Excel. Excel is a great RF development environment for anyone who knows how to use Excel. You can throw this lot together, just get some trial numbers, play with it, and plot the graphs, and you can see all this going on in front of you. So if you want to test out an algorithm and you don't want to go as far as GNU Radio, Excel's, well, a bit unusual, but it does work. Okay, so we're adding two signals. We're making one of the images cancel and the other one we want to keep. But there are going to be errors, and this is where a lot of the problems, I think, with SDRs are going to come in the future, that what you get out isn't perfect. So there I'm just showing the example that we'll have a phase error and we'll have offset errors, and we'll also have a gain error. So in this case I'm saying that our Q will be slightly different, C, compared to our I in terms of its magnitude. These all mix together and you get a bit of a problem. Some simple mixers, you've got a 28 dB image rejection, which is nowhere near good enough, right? You need a lot more than that. But software can come to the rescue. You can measure these things. You set up your radio, you run it, you can give it a known tone, a beacon perhaps, and you can work out what's going wrong. You know the beacon is just there, you know there aren't images in it. So you can calibrate it, and unfortunately these calibrations tend to be frequency dependent, but most of the SDRs you'll see, they have inside them a big table of corrections against frequency, and they will correct them for you. And you can get the images, as I say, down to 80 dB or better, so it's still not perfect, it's still not as good as you will get out of some really heavy filtering, which is why I said earlier, you're probably going to want to put filters into your system, but it is a lot better, and with some careful choices of frequencies, IQ mixing can give you some quite successful splits, so that you can then filter a long way out from where your images are. Okay, I added this one in. I gave this talk a little while ago at Martlesham, and somebody said, what about dither? So I thought I'd add in something about dither. Supposing your input signal is less than a single bit, so you've got this really weak signal, but you want to actually see it. And there's an example. The red and the green lines are just there arbitrarily representing where I would have a different level for my ADCs, 1 bit difference. And if I add some noise to it, you can see that it will start to go over the, actually I'll use the pointer here, can't I? So you will get some values above and some below and a fair bit in the middle. But it will have all this noise superimposed on it. And we'll have a look in a bit. Obviously, we can filter that, but when we look at decimation, we will see that we can actually regain all the information from that signal as long as we can see some of it. So, what can we do in software? Now, this might be on our PC if we've got a direct conversion, or it might be in an FPGA sitting there in our actual hardware. Actually, neither of those have got FPGAs in them, but somewhere we're going to want to be doing some software processing, and this is what SDR is all about. We can do almost every type of filter. If you can think of it, you can probably come up with a digital design filter. We'll talk a little bit in a minute about digital digital synthesis. That's easy for me to say, which is basically just creating a sine wave, a cosine wave, by just picking numbers and following along the graph. So we're doing this all in software. There's no real generation of the sine wave. It's just we generate the numbers that would look like the sample train. Mixers, we've already talked a little bit about those. Sample rate changes, so we've got mega sample per second coming out of our radio. We can convert it into something much slower that we could put into a speaker, for instance. Amplifiers is just a multiply. Level shifters is just a subtract or an add. FFTs, we'll talk a little bit more about those in a minute, transferring from samples in the time domain to samples in the frequency domain. So then we can do some interesting filters. The CIC filters, if you ever get into SDRs, you'll hear of them a lot. They're doing a lot of stuff all in the same place. One filter that does integrations and rate changing and filtering all at the same time. Obviously, we can do all the modulations you can think of, and it just keeps going. Thing to remember, always we have delays. In the digital domain, we need a number of samples to do anything. If you have to count some samples, then they are going to be, that's incurring a delay because you can't do anything with an output until you've got enough samples for your input. So if you've ever looked at an SDR and a real voice signal, compare them back to back, you will hear SDR sharp, for instance. You've got half a second of delay, which is enough to be confusing if you're trying to listen to two things. So that's a problem. It's something that people put a lot of effort into trying to overcome these delays. So I talked a little bit about filters. I'll just go into a little bit of detail here. Most filters are represented graphically by this kind of, software filters by this kind of diagram. All we've got here is we've got a sample comes in. On the left-hand side there, we multiply that number. It's just a sample. It's a number with some constant. And then we sum it on the bottom right-hand side, and we have an output. The next sample comes in. We move everything along. It's a shift register. So now sample 1 is in the position 1, and our first sample has moved on. Let's call that sample 0. That's now in our second position. We do the multiplies by the constants, we add them, we shift it again, we keep going. And by choosing the constants, we can do different filters. So sine wave, low pass, high pass, band pass, all just multiples of these things with different constants in there. And we'll look in a minute or two, you can do some really complicated transforms that are technically filters, but not as you would know it in the analog world. But yeah, so if you see Z1 in a box in a diagram, it just means a 1 clock delay, basically. And so this thing is a lot of delays, i.e. it's a shift register. So interesting, and if you get into this, you'll see that sort of thing. DDS, as I said, it just generates samples. So here's an example graph of some DDS stuff, just a simple sine wave. There are lots of ways of doing it. You can do it with lookup tables. There's this rather nice algorithm HP invented a long time ago called Cordic, which is a very quick way of doing these things, and it's very powerful. So if you wanted to get into DDS technology, Cordic is a good, interesting place to start. Okay, decimation. This is getting something for nothing, or in SDRs, it's getting a lot for nothing. So if we reduce the bandwidth of a sample, we can actually then get more data bits, get more dynamic range out of it. Here's an example. We take a signal, it's 14-bit sampled. If we take its bandwidth down by a factor of 100, or sorry, a factor of 1,000, from 20 megasamples down to 19.5 kilosamples, we'll add 9 more bits. We get a start with a 14-bit. You remember that was an 89 dBFS. Not very good. But when we add 9 bits, we've got 140 dBFS. And that's beginning to be better than almost any of the off-the-shelf radios you're going to get. So here's an example. I've got a 9-level ADC, so it's a bit rubbish. And we're sampling a 1 hertz signal at 1 kilohertz. So we're getting a lot of samples, but they're almost all the same thing because it's very low resolution number of bits. So if we just do a moving average, simply adding a certain number of signals together, it goes through. I've rescaled it to 1, but here we've got a moving average, and that's all I've done, just added groups of numbers together for a moving average. Now, if we look at that and say, well, let's add every 10 samples together, now we've got something, I don't know how many different levels there are there, but it's 20 or 30 levels where we started with 9 at the beginning. And that's decimation, and that's why SDRs can be useful. Because without this, it's called process gain in the software world, even a very good SDR is still not going to be giving you anything like the dynamic range of your normal receiver. But with this technology, as you can see, we can easily exceed on a 6-pound radio. We can have a dynamic range that rivals the ICOM radios. Okay, I mentioned the filters that you can do with that Z thing, the shift register. This guy, David Hilbert, he came up with a great bit of technology. He came up with a lot of stuff, actually, but one of the things that he did was he said, if you give me a sine wave, I'll give you a bit of software that will basically translate it to two signals at 45 degrees plus and minus of where you were. This is a 90-degree phase shift between the two signals. This is the way of generating an INQ signal source for the sine and the cosine that we wanted to use to mix. So if we start off with the signal, the blue one, and we put it through the Hilbert transform, we will get a plus 45 and a minus 45 shift out of that transform. So that gives us now the two signals. We can use those to mix with what we were doing earlier with our input frequency, and now we can do the plus and minuses to get upper sideband or lower sideband, get rid of those images. Okay, a little bit on fast Fourier transforms. We start off with our samples. We've got our ADC, it's just sampling in time. So we've got samples and a time, so effectively voltage, let's say, and time. We want to convert those into a power or intensity against frequency. We can use this thing called the fast Fourier transform. It's a very nice piece of software, all based on maths. Or if we only want to do part of it, we can use this thing called the discrete Fourier transform, which is much, much faster to do much less data. It's quite computer intensive, so when you start to see spectrums on the screen, there's a lot of work going on behind those. That's not the sort of thing that your Arduinos can do. You're going to need PCs, or at least your Raspberry Pi or something like that. Everything runs faster in powers of 2 on a computer, so you'll see Fourier transforms using 1024 or 512 samples. And so here's the big delay. If you want to see 1024 samples, you've got to read them all in first. Then you've got to do your Fourier transform. Then you've got to put it on the screen. So that's why most spectrum displays are lagging behind when they're being done in software, because there's some big delays involved and processing time taken up. So when we do this, we end up with a histogram. Here we started with a 1 Hertz signal. In the frequency domain, that means we have something in 1 Hertz and nothing elsewhere. And these buckets along the bottom, the categories that we're putting the data in, they just basically are filled by the FFT. And if we do an inverse FFT, we would take the data and map it back into the time domain. So, yeah. So let's look at a little bit of simple signal processing in the frequency domain. So we've got some software, we can convert our signal into the frequency domain. Here I've got a fairly complicated signal. In the frequency domain, I've got some white stuff, which is noise. I've got some green stuff there, which is the signal I actually want, and I want to shift that down to 0. That's my SSB signal, upper sideband signal, shall we say. And I've got a nasty red one there, which I really want to get rid of. So because these are just numbers, it's just being stored as a set of numbers in a histogram at this point in time, I can just set the ones I don't want to 0. I just filtered it just like that. Just go through that array of numbers and just say, right, I want zeros in all these things. And it's gone. It's that simple. So I've done my bandpass filtering just by going through that array of points of histogram values, setting them to 0. Now I can just say, well, I'll just move them all down. So I'll just say, well, whatever band it is I wanted, I'll just put that in the 0 bucket, the first bucket, and so on. And now I've shifted it. So I've just demodulated and filtered in the frequency domain in very, very little effort from software point of view. Then it's just do an inverse FFT, the reverse process, the reverse algorithm, and I got my signal back, and that would be it. And that is the way, or part of the way, that quite a few DSP systems are working now. So that's one way of doing it. There are others, of course. We've got all these filters we've looked at. So we could do all the filters in the time domain with that shift register thing. We can mix with frequencies. We've got our DDS, our chordic algorithm, can generate some frequencies, so we can just mix with that. Mixing in software is just multiply. 2 samples multiplied together, frequencies are mixed. How are we doing for time? Okay. So I wanted to say a little bit about GNU Radio. So what's good about it, it's free, it's open source. If you're interested in any of these algorithms we've talked about, any of this processing, you can just go and look and see how it's implemented. If you know anything about this, what I've just been saying, it's very, very easy to use. Graphical user interface, I'll show you that in a minute. Literally, you just pick and place blocks, and rather than spending 3 hours with a soldering iron, you just pick this thing up, drop it on the window, and it's there, it's done. I'll show you how it works in a minute. It's available for Windows. I've got it running on Windows in a minute. It was originally written for Linux, and it does run better on Linux. So if anybody feels adventurous, wants to go and play with Linux, GNU Radio, it's quite easy. It's installed on most distributions these days. And you can run it on Macs. You can run it on bootable USB drives. Lots of ways of getting into it, and it's free. So it's a good place to play. So that's what it looks like. It's a bit daunting, but actually, I think we've got some controls across the top. We've got cut, copy, paste, all that sort of thing. You're probably familiar with those things. Down here, we've got all the things we can do. So we can do math operators. We can do NOAA satellite decoding. And all these things. We can look at audio sync. That's actually the speakers. We're just going to put data in. It's going to come out as an audio signal. We're going to hear it. We've got multiplies. We've got low-pass filters. And if I want to do one of these things, I would click on here. I would get one listed, and then I would just double click on it, and it'll appear as a graphic entity. I can just grab one of these outputs and inputs, the orange boxes, and I just connect two together by clicking twice, and that's me wired it up. So this little guy, what does he do? He starts with a signal source. In this case, it's just generating a frequency, but it could be an audio source, which is a microphone. I filter it, I multiply it by another frequency, and that frequency delayed, which in the time domain means my sine and cosine. You might recognize this 1.5 kilohertz in here, because this is actually a Weaver demodulator, or sorry, Weaver modulator, third method SSB modulator. For those who know about that, once you've mixed it, you just low pass filter the two, and those are your two SSB signals, I and Q, that you're going to send out to the next level. Andy Talbot, are you in here, Andy? No? No. Andy Talbot said in Radcom about 2.5 years ago, he said, it'd be really nice if someone could write all of this in C. Well, it took me about an hour to write it all in GNU Radio, and this actually works. If we ran that thing and we had the microphone plugged in and we had some speakers plugged in, we would actually hear baseband SSB Weaver modulation coming out, ready to go up to whatever SSB radio modulator you wanted to put it in. So it does work, and it's I say it's very easy. You can learn this thing quite quickly. Just a bit of a zoom in on that. Obviously, you have to worry about your signal rates. So the audio sync has a particular sample rate that it expects. Most audio systems are 44.1 or 48 or whatever. And there's a low-pass filter I have in there. It's got a gain, it's got a sample rate again, and this is a 3.5K cutoff with a 100 hertz transition. That basically is defining how sharp the slope of the filter is. And time sync, that's just an oscilloscope on the screen, so you can look at it. So very simple things. Here's an example when I open up this thing. So I want a bandpass filter. I just go on there, double click on it, a bandpass filter has appeared. And yeah, and there we go back with that Weaver modulation, which, as long as you know what you're trying to achieve, you've got to understand the design behind it, but actually implementation of it is very easy. One other thing you can do here, if you want to just record your audio and have it in a file, you can have a file source, and you can take away your audio sync, and you've got a simulation, and it'll simulate a lot faster than it will run in real time. So you can try your stuff out, you can see if it looks right, and then save yourself a lot of effort with design later on. So the output of that one, we've got our two signals at the top, 1.5 kilohertz separated by 90 degrees, and our two modulated signals, I and Q, at the bottom. So here's another one. This one I'm actually going to run for you, hopefully. We start off with a thing that talks to this RTL dongle. We low-pass filter it. We convert the signal rate from the two megasamples that come out of this one into the, oh, this thing's giving up on me, into the something that we can put into a receiver. So the rational resampler is just basically slowing it down. Wideband FM receive, single box. You put in your I and Q signals, you get out a demodulated FM signal. So then I'm being a bit sneaky. I've created a 1.5 or 1.7 kilohertz interfering signal. I just add it in. It's just an addition, simple as that. I go through a band reject filter. Now look at the numbers on that. This is where it gets interesting. So this is a band reject filter with a 10 hertz brick wall filter. So what I get out of this will be the audio samples with a little 10 hertz gap in the middle where I've taken out my interfering signal. So with a bit of luck, I can get this guy here. So it's not quite the resolution that we had earlier, but there is basically that that diagram. And I will just disable this guy. No, I won't, sorry. I will bypass this guy. So I'm not going to do the filtering to start with. So what you'll hear, I hope, is okay. That's disappointing. It works fine downstairs. Does it need... It is classic FM, yes. But, yeah, okay. Right, classic FM with a really annoying thing in the middle. And I'll just put in that 10 hertz wide brick wall filter and run it again. So that is really classic FM. I'm acting as an antenna here, but and there it's gone. And that you can't do with your icon. So will it just let me do any questions? Silence. Ah, a question. Do we need a microphone or we should shout? Oh, okay, there we go.
When you're doing these things with the GNU Radio,
Yes.
how do you know how much you're going to load the processor you're going to run it on? Can you simulate various processors or what?
When you run it on a PC here, you can just look at the task manager for the performance and it'll tell you how much your processor you're using. The most things that we're doing here, that demodulator is trivial. The processor won't notice it's doing it. If I put an FFT display, and you remember I said FFTs are quite processor intensive, you'll get up to about 10% on this PC, which is quite a good spec PC. You'll get up to about 40% for that same example on a Raspberry Pi. If you want 4 or 5 FFTs, you'll start to fall over. Mostly, though, it'll fall over in that it won't display the FFTs as fast as you've asked it to. It will still be doing the demodulation. You will still hear the audio. And you have to really add a lot of features in before you'll slow the thing down to the point that it stops working.
Is it possible to show us briefly what an example piece of code looks like in one of those boxes? Is that doable, or point us to some resources where we can go and have a look if you're interested in...
If you go on the GNU Radio site, which I think, gnuradio.org, they have everything you might want to in there. It is all open source. The first thing you would look at is the Python code that calls in all those modules. So you won't see what's in the modules, but you would see the top level code. And you'll be surprised about how small it is. That is about 15 lines of code. It's just really, it is saying hook this module to this module to this module, and that's all it does. And you can see it very clearly. I have a sample rate variable in there. It's declared as a simple Python variable. And if you had, for instance, you had a Raspberry Pi, you had say a rotary encoder on it, you could just change that figure there and then. And obviously, you've got to be into the Python programming or C++. You can link in all sorts of things with this. But yeah, you can find it all on there. And Some of the modules are written in C++, a little bit harder to understand, but optimized, and particularly the ones that you'll find filters and things like that. They really are very efficient implementations.
Yeah, I'm not sure whether you necessarily.
Hello, I'm not sure whether it's really necessary to do it, but presumably you could write the code on that, put it onto a Raspberry Pi and put the dongle into it and
Yeah.
get the same effect.
Yep. Yeah, the Raspberry Pi will run all of this quite well. Yep.
Hi. You give a couple of examples of filters there. You mentioned one of them in the time domain, and then another one in digital in the frequency domain with an FFT.
Yep.
Why would you choose one over the other? Are there different? What are the compromises that are being made there?
The time domain filtering is much quicker because you probably only need, let's say, 9 or 10 samples for a not particularly good filter before you've filled up that shift register. And then you get for every clock, you get another sample out. So you've only got delays of 5 seconds, and it's very easy to implement. If you need to go to the frequency domain, now you've got to do an FFT, process the data in that block, IFFT back into the real world, and then do stuff with it. And the FFT is, roughly speaking, a square law process. So if you've got 1,000 points in your FFT, you have 1,000,000 processes to do to get to the Fourier, to frequency domain, and then another 1,000,000 to go back again. So we had 9 for a not very good filter in the time domain, and we had 2,000,000 for a very good filter in the frequency domain. But, and this is where it can be really interesting, once you're in the frequency domain, you saw how easy it is to do stuff. Set things to 0, you filter them out. Move things to a different position, you've frequency demodulated. There are a lot of things that you can do. So if you're doing a lot of processing, sometimes it's going to turn out that it's actually easier to do the FFT once, do all the processing, then come back again. And there's some really nice stuff people have been writing to run on NVIDIA graphics boards, where you've got literally thousands of processors. You can do all that FFT really, really quickly because you do it all in parallel. Then you can crunch the numbers and then put them all back in parallel again. So it's really about what is right for the processing. At the moment, most people are doing it in time domain, but there are some very nice, powerful examples of people doing things in frequency domain. Down here.
That demonstration that we saw was a sort of workbench type prototype. Is it within GNU Radio the ability to have a GUI user interface and link the two together? In other words, that filter, could you turn it on and off just by pressing a button somewhere? Is that easy to implement? That's really all I want to know.
It is. There's a lot of possibilities built into GNU Radio to do these things. I have just this one here, which is my tune box, top left hand of the screen. So when I run it, that appears. That's all I've got as a control for this because I just wanted to tune it to find a radio station. But I could add in sliders into there. I could add in displays, FFTs, oscilloscopes. They're all there. There's a couple on the screen there, but yeah, they're all there. We can just drop them in and get them going. And there are a couple of people. I don't think ETUS actually use the GUI front end. Do they do it?
Sorry, can I? There are a number of examples that ship with GNU Radio that are meant for use with ETUS USRPs.
Yeah.
The UHD FFT, for instance, uses the graphical front end. And yeah, there are switches, buttons, etc.
And it can look quite good. And you can add your own.
So as an example of a GUI that is entirely implemented or entirely based using GNU Radio, but then with some custom front end is GQRX, which is written by Alex, who's giving a talk quite soon.
Okay. Great.
Any other?
Oh, no, one more.
One in the corner.
Hi, I was just going to say we've got a demo on the Martin Lynch stand with SDR Play, an RSP2 running GNU Radio if people are interested in the coffee area. Just for today, not tomorrow.
Okay. Yeah, we've finished. Yes, we're done.